All right, so today we will basically show the example for LU decomposition. So just a quick overview. The reason why we want to do LU decomposition is in cases where I'm solving a lot of systems, AX is equal to B, that have the same A. Okay? So same A, in different right-hand side B. And a lot of engineering problems do come in that form. And what it's actually saving us is that the process of LU decomposition will decompose A into a multiplication of L and U, L being a lower triangular, U upper triangular matrix. And that in that case, I'm actually doing the forward elimination step of Gaussian elimination only once. That is the expensive step. That's the way I quantify it is O of n cubed, meaning order of n cube operations being multiplication and addition and division and so forth. Okay? And that order basically scales with the size of matrix A. So of course, if I can try to go cheaper, I would like to go cheaper. If n is 1,000,000, okay, n to the cube is 10 to the 18. Okay? And 10 to the 18 is a lot. So if I can cut them down, that would be great. Back substitution is the next step that I need to do after I already have this. And that's much cheaper, so I will actually, for all of the subsequent, so when I'm solving this for multiple right-hand sides, I'm going to be replacing this forward elimination, the expensive step, with the cheaper ones, two cheaper ones, one forward substitution and one back substitution, and both of them are O of n squared. So in case of n being 1,000,000, that's 10 to the 12. 10 to the 12 is a lot cheaper than 10 to the 18, trust me. To the point that sometimes I'll be actually able to solve something that I thought I couldn't. Okay. So the way it works is I will first do forward elimination, and I will do our forward elimination as we're used to doing it and get this upper triangular matrix. It's just in the process I will actually record the coefficients that will actually give me this lower L, matrix L, that is a lower triangular. So nothing that you don't know, everything that you really do. And then after that, I will solve two systems. For one, I'm going to find vector D, such as LD, such that it solves LD is equal to B. So I'm going to solve a system by forward elimination. And then after that, all I'm solving is UX is equal to D. And I'm pretty much done. So let's actually do that example, so it's going to be much easier for you to follow. Okay. So the example we're going to solve is as follows. LU decomposition. So basically the procedure in LU decomposition, when I have AX, I'm solving AX is equal to B. Step one will be forward elimination. To solve A is equal to, or rather to find, rather than solve, and basically L is lower triangle, and U is upper triangular. And then the second step is for right-hand side B or any number of right-hand sides B. So if I'm solving multiple systems that have different B's, I'm going to repeat this step multiple times. So for every right-hand side B, we do the following. We solve LD is equal to B to find D. And this is forward substitution, so it's very similar to backward substitution. And then we solve UX is equal to D. So once I have D, basically I plug it in and I find X. So basically to find X, that is backward substitution. And then I have X. Okay, let's do it. So my system that I'm solving will be minus 3, 2, minus 1, 6, minus 6, 7, 3, minus 4, 4, x1, x2, x3 is equal to minus 1, minus 7, minus 6. So what I'm going to do forward elimination, and I'm just going to be careful to record all of the coefficients that I'm multiplying different rows of A with, and that will actually assemble our matrix L, and U will be the product of that forward elimination. Okay? So there's nothing really new other than recording the coefficients here. So let's do that, and then I'm going to backtrack and explain to you why is it actually working. So if I had this matrix A, what it is that I would be replacing, so basically if I'm doing forward elimination, right, I can actually I don't have to work with augmented matrix, I can just work with matrix A. So essentially, I would be using, this is my first pivot element, I would be using it to eliminate these two elements. Right? So, well, let me actually just go, shall I start by the lower? Let's start from the front row first. So Gianfranco, you're going to be the first. So what do I need to do to eliminate this number 6 here?
You can multiply the first row by 2 and add them.
Yes, so basically the coefficient officially, I'm gonna, one of the positions, and now I'm just gonna be careful to do always a similar thing, okay? So we're not like going all over the place with the coefficients.
2 minus A21 over A11 times first row.
Okay, so now I'm gonna actually using this rule, okay, just to stay consistent, and basically I'm gonna record this coefficient. I'm gonna immediately give it the name L21, okay? So my L21 is actually 6 divided by minus 3, so it's equal to minus 2, okay? So can you basically do this operation? So I can, and I'm gonna change sheets, so I hope you have it written down. So when I do that, what do I get? So I'm replacing the second row with 2 plus 2 times first row, right? So it's 0 here. it's minus 6 plus 2 times 2 is
It's minus, so it's plus 4, so
minus 2. And then I have 7,
plus 3 is 10.
it's 7, 2 times minus 1. So it's actually 5, right?
It's minus 2 is
It's plus, minus 2. Yeah, it's going to be negative, so it's minus 2. 7 minus 2 is 5, right?
no, isn't or 1 minus 2.
Let me go. I have notes differently. So I have minus 3, 7 plus 2 times minus 1.
7 minus
Minus 2 is plus 2 times minus 1. Right? So it's 5. I gotta make sure too, because sometimes my notes have issues. All right. And then what am I going to replace? I don't have now the view.
It was 3 negative.
It was 3. Okay, so I'm going to replace it by it was basically 3 minus 2, you're saying, or plus 1?
3 minus a11, or 3 minus a31 over a11 times rho 1.
Okay. Which comes down to 3.
And the coefficient is just negative.
Mm-hmm. So this is my coefficient that I'm going to record as L31. Okay. So that's this. And when I do that, can you add them up for me, please, first? This is a 0 as it should be.
-2, so 6, and 3.
I had minus 4 plus 2. That's minus 2. Because this is minus is plus.
Oh, sorry, I was
Huh? And 4 minus 1, 3. All right. So now I continue the procedure. And now I need to eliminate this. And this again, I'm going to eliminate by doing replace by 3 minus A32 divided by A22 now. This is my new pivot position. So this in this case is 3 minus 2 over minus 2, 2. So it's just 3 minus 2. And my coefficient that I'm remembering now, this is now location L32 is equal to 1. So basically the result, once I do that, Barun, can you?
Okay, tell you the third row.
Mm-hmm.
0, 0, and negative 2.
-2. So this is my upper triangular matrix. Oops. So that is actually U I'm looking for. And my lower triangular matrix, L, it has these, so I had that L21 is minus 2, that one I don't have on this page. And L31 is minus 1, L32 is 1, okay? So I'm actually going to place them precisely in those positions. So L21 is going to be minus 2, minus 1, 1. I'm going to place 1s on diagonal, and that essentially gives me my lower diagonal matrix. Let's check that it actually works.
Wait, could you repeat again where
That is my L21 that I recorded in the first replacement I did.
Okay.
Okay? So when I was eliminating the position 2-1, I recorded L21.
Okay.
When I was eliminating position 3-1, I recorded L31. Those are the coefficients I'm recording. And this time I'm doing it in a systematic way. I'm always using that 2 minus A21 divided by A11 rule. Okay? Instead of minus rho plus A21 divided by, so I could do variations of that if I was just doing forward elimination. But now I'm just using the strict rule, so always the same, so I record them correctly. And L32 is 1. Okay? So now let's actually check that it works. So my L, I claim that L is 1, 0, 1, 0, 0, minus 2, 1, 0, minus 1, 1, 1. There's my L. My U is, oops, it is minus 3, 2, minus 1, 0, minus 2, 5, and 0, 0, minus 2. So L times U is minus 3, 2, minus 1, 6, minus 6, 7, 3, minus 4, 4. That is indeed A. Okay. So now I have my LU decomposition. So it's just forward elimination with some recording on the way. So now I'm going to actually solve system. So step 2 is solve LD is equal to B, and then UX is equal to D. So LD is equal to B is an upper triangular system. Is system 1, 0, 0, minus 2, 1, 0, minus 1, 1, 1. I'm going to call this D1, D2, D3 is equal to B. What was my right-hand side? My right-hand side was minus 1, minus 7, minus 6. Okay. So basically from the first equation, Logan, what do I get?
Like solving for D.
Mm-hmm.
Do you want to? Sorry, do you have to keep doing it that way, or can you just like augment it?
But now we are already in a lower triangular matrix. So this is where I'm using substitution. If I have upper or lower triangular matrix.
Oh, so.
But I could, yes, I could, but.
So could you just say like D1 is -1, and then
And then keep going. So question here is, could I just augment this matrix and solve? Yes, I could. But for forward or backward elimination, since I already see D1, I can just, right? So D1 is minus 1. And then I have minus 2 D1 plus D2 is equal to minus 7. So it gives me that D2 is equal to?
Sorry, wait. Would D1 be
-1, correct. So this is 2 on the other side, so my D2 is?
How'd you get D2 equal to -7?
Minus 2 times D1 plus 1 times D2 is equal to -7. That's my equation 2.
Right, and then you drew the arrow and you have D2 equals -7.
And then what else?
Oh, sorry.
I'm waiting for you.
Okay. Plus 2 times D1.
Mm-hmm.
And then you know D1 is -1. So you could just say, yeah, so you could just say -2. So.
Okay. And then third, what do I get from third one?
So,
Mhm.
negative D1
I'm gonna just verify from my notes. All right, very good. So now my next system that I'm solving is ux is equal to b. So my u was minus 3, 2, minus 1, 0, minus 2, 5, 0, 0, minus 2, x1, x2, x3 is equal to d. So d1 was minus 1, minus 9, 2. So how do I solve that one? Easy. Good morning. What do I do here? This is upper triangular system, so I can just do backwards. So what does it give me for x3? And then person next to you, how do I get x2? I know Hamid Reza knows, so I'm gonna. Yes, questions? So now I'm solving ux is equal to b. B being my original right hand side, u is the upper triangular matrix I got in the first.
But you plugged in
Yes.
or for D.
Equals to d, actually, that's what it's supposed to be. Sorry. So this d that I just found. So how do I get x1? I'm going to squeeze it in here. Minus 3x1, 2 times 2. Huh? It's minus 2 minus 6 over minus 3 is 2. Right? Yes? So that is our solution. Let's just review once again why is this process the way it is. So these are the steps. Steps seem relatively straightforward if you write them down and just follow. So what was this process relying on? It was assuming A is equal to LU, where this is L lower and U upper triangular matrix. Okay. And I am solving AX is equal to B. AX is equal to B is the same as AX minus B is equal to 0. So LUX is the same as AX, right? Minus B is equal to 0. So now, if I find D such that LD is the same as B, I can replace B with LD. So then I have LUX minus LD is equal to 0. So it's L times UX minus D is equal to 0. In that case, the x that I'm looking for is solving, this has to be 0, right? This is something non-zero, it's a matrix that is multiplying this. If I want to, I can just multiply with an inverse, okay? From left. In matrix multiplications, it's important whether you're doing things from left or from right, because AB is not equal to BA in matrices. So when I do that, my UX that I'm searching for is solving UX is equal to D. So X that I'm searching for so essentially, once I solve this step, which was my step 1, okay, then all I need to do is solve this and solve this, which is what we did, and I will find the solution X for this problem. Is this okay? Questions? Now the only question is remains, can I always do that LU decomposition? But that's what we've been doing. We've been I know that I can transform the matrix A into that upper triangular form. The only problem I might run into is that I'm going to get one of those rows of zeros, if you remember, for A. Okay. In which case, it means that my A doesn't have an inverse, so I don't have a unique solution to the system, and that will kind of stop this operation. Okay. But in case my A has an inverse and I have a unique solution to the system of equations, x1, x2, x3, we know that in 3 by 3 case, we're looking for intersection of 3 planes, right? Sometimes planes are parallel, so you can't find that intersection. But if I can, I'm going to actually be able to employ this procedure. Now, just going back a little to that A, so if you think about it, what I did there, A is equal to L, and I said I have ones on diagonal, and then I have L2, 1, L3, 1, L3, 2. And let's say I had that upper triangular, I'm going to do a little more general. U1, 1, U1, 2, U1, 3, 0, U2, 2, U2, 3, 0, 0, U3, 3. So this is my A. So I'm just going to show you for this A21. So this is matrix multiplication. Okay? In order to get this element here, A21, I have to multiply this row with this column, correct? So when I do that, I'm going to have L21 times U11 is equal to A21. So L21 is A21 divided by U11. But in my process of forward elimination, my first row never changed. Okay? So U11 is the same as A21 divided by A11, and that's precisely what I recorded as L21. So this is why recording L21 as A21 divided by A11 works. And essentially, if I didn't set these to 1, then I wouldn't have sort of a unique solution. I would have multiple possibilities. And this 1 means I'm leaving the first row unchanged. Okay? So obviously, if I multiply these two, I'm going to have U11 is equal to A11. That means that I didn't change the first row. Now the others, you could do this too. It's just that, remember, in forward elimination, I'm actually changing things in place. So these A's are, but you could recover that these are actually correct the way we were recording them as well. Okay. Questions about LU decomposition? One case where you could actually solve this or use this to find the matrix inverse. Okay. So how would I find, this is just, I think you have one, may as well actually continue to find matrix inverse here. So if I have matrix inverse in this particular case, how would I find matrix inverse? Let me actually just quickly check that this particular matrix that we are solving for has a nice inverse. Minus 1/3, 1/3, 2/3, 1/4, 3/4. Yeah, this is nice enough. So these numbers are okay enough, okay? All right, how would I find matrix inverse in this particular case? So what I'm really looking for is matrix such that A inverse is equal to identity matrix. And I'm actually gonna, so my A2, A11, A12, A13, A21, A22, A23, A31, A32, A33. And I'm actually just gonna present this inverse matrix as a matrix of columns. Is equal to identity. So I know if I was just doing this multiplication here, the way I would proceed to get the multiplication is I would take the first row of A, I would multiply it with the first column, right? And I'm going to get this position here, correct? Then I would get the second row of A, also multiply it with this first column, and I would get this second position here, 2, 1 position, right? And then for 3, 1 position, I would take third row of A, oops, wrong color. Or rather, I was supposed to change color here. I would take third row, also multiply by this, and I would get this position. So effectively, this product here is matrix A times x1, matrix A times the second column, x2, and third column here. So this is just matrix multiplication. Is this clear? So basically this is how I would multiply matrices. So essentially, to solve this problem, or to find this matrix A inverse, which I represented here by columns, I essentially have to solve three systems. AX is equal to this first column. AX2 is equal to the second column. And AX3 is equal to this third column. So I need to solve three systems in order to find columns of A inverse. So columns x1, x2, x3 of A inverse. Is this part clear? So I already created decomposition A is equal to LU for the matrix A that we just dealt with a moment ago. Okay? Let's find its inverse. So I already have A is equal to LU for the matrix A, which is minus 3, 2, minus 1, 6, minus 6, 7, and 3, minus 4, 4. Okay? We already have A is equal to LU. So we already have now all I need to do to find x1, x2, x3, these column vectors, is all I need to do is do okay? All we need to do now is we said find LD is equal to B, and I'm going to call that B1 and LD1, which is 1, 0, 0. Okay? And then UX1 will be this D1. That's the first set of systems I need to solve. And then LD2 is equal to 0, 1, 0. And UX2 will be this D2. That's the second set of systems. And everybody's like, oh no, 3 sets? Yes, 3 sets. LD3 is 0, 0, 1. And UX3 is this D3 that I find here. Now if I had a large matrix, okay, if I had a very large matrix A, I would have gone through that forward elimination 3 times, or 4 times if we count in the first system that we solved. Okay? 4 times n to the cube for large n is much larger than doing that n cube of operations once and then just repeating these are O of n squared. Okay? So let's assume, why is this so much cheaper, right? It's cheaper in this case, so n is equal to 3, so essentially O of n cube operation for forward elimination is replaced here with 3 times, or 2 times in each case, 2 times O of n squared operations, because both of these are n, scale with n squared. And that's what's cheaper. It looks like now, oh my, I have to solve a lot. but if I was actually doing all of the things by foot, and that's cheaper. Let's do at least this first system and find the first column. So where did I stop? You're next, so I'm solving this L. What was my L? It was minus 1, just 1. 1, 0, 0. Minus 2, 1, 0. And minus 1, 1, 1. Times D, I'm going to call it D1, D2, D3, is equal to 1, 0, 0. So my D1 is easy. It's just 1. Let's go for D2. So D2 is 2. And then what is D3? D3 is negative 1. So what's good about these systems, and you can see, is that because I have very simple right-hand side, and I have ones on diagonal, solving this goes really quickly. Okay, so it's really simple operations. So next, so what am I solving for now? 0, 1. 0, 1, 0. So I have no. So now I'm actually going through ux is equal to this d that I found. So that is u was what? U was, where's my u? Minus 3 to minus 1. And now I'm solving for this d1, 1, 2, minus 1. So now I'm here, okay? Because I just found this. Okay? So that was this process, was finding this. So, and let me actually outline those. So these, that's this. Okay? So what is my x3? One half, okay, and then can you do the second one for me too, because this was easy, right? So what is x2? Yeah, so x2 is, and next to, how do I get x1?
So negative 3x1 plus 2x2 minus x2 is equal to 1.
I'm already plugging in just to be faster. Okay. So this is my first column of my inverse, matrix inverse. And I would repeat this first time to get my second column and third column. So essentially, oh, 7. So my A inverse, the first column we have just found, and it's minus 1/3, 1/4, and 1/2. And there is this other two columns that are right now missing, and if I solve two more systems in these two steps. So they are relatively fast systems to solve. Now, what will I be measuring here on the test when I give you an example like this? accuracy. So you have to do a couple of problems like this just to gain speed and that you don't make small mistakes for this.
This would be by.
Fine. All right. Questions? So for inverse, you use LU decomposition. What is your question? So that's a possibility. I could ask you to program some of these. Okay? So one variation could be during Gaussian elimination, record matrix L. Okay? And then the output could be matrix L and U. So that's essentially LU decomposition. Okay? So you could program it.